When the third interstellar object ever recorded by human instruments rounded the Sun in late October 2025, it started releasing material. And almost immediately, every instrument pointed at it returned numbers that did not belong in any known catalogue. The water vapor production rate reached levels on the order of hundreds to thousands of kilograms per second near perihelion, enough to fill tens of Olympic swimming pools every day at peak activity. And the water itself was chemically anomalous. It carried a form of hydrogen so rare in our solar system that the reading sat 40 times above the value found in Earth's oceans, and 30 times above any comet ever studied orbiting our Sun. The comet was soaked in methanol at levels that placed it among the most alcohol-rich objects ever observed, and when X-ray telescopes swung toward it in late November, they picked up a faint glow extending hundreds of thousands of kilometers from its core, the first time an interstellar object had ever been seen shining in X-ray light. Across the solar system, spacecraft that were never designed to study comets broke from their primary missions to look. A rover on Mars caught a faint smudge in the Martian night sky. A Jupiter-bound probe diverted 5 of its instruments. Telescopes on Earth, in orbit, and deep in interplanetary space all converged on the same target, and what they collectively found in the chemistry of this single icy wanderer is already reshaping what scientists thought they understood about how water, ice, and the raw ingredients of worlds behave around other stars. Each of those instruments was reading a different wavelength, a different molecule, a different physical process, and none of them was built to answer the question this comet was raising. The picture only came together once you laid the readings on top of each other. That's the shape of the story from here. No single measurement was decisive on its own, but the pattern across all of them was. This is what came out of 3I Atlas and why it matters. On the night of the 1st of July 2025, a telescope in the Chilean desert flagged a faint point of light moving through a crowded patch of sky near the border of Serpens and Sagittarius. The telescope was part of NASA's Atlas network, a system built to watch for asteroids that might threaten Earth. And the object it had just picked up was sitting at magnitude 18, far too dim for any human eye. But its motion was unusual, and within a day, trajectory analysis confirmed what the speed and orbit implied. This thing was not bound to the Sun, it was passing through. The Minor Planet Center made it official on the 2nd of July, designating the object 3I Atlas, the third interstellar visitor ever confirmed. The first had been Oumuamua back in 2017, a strange elongated body that arrived with no coma, no tail, and no clear explanation for the gentle push that was accelerating it away from the Sun. The second was Comet Borisov in 2019, which looked much more like a familiar comet, but was small and faint and gave scientists only a limited window. 3I Atlas was something else entirely. It was bright, it was active, and critically it had been caught early, 4 full months before it would reach its closest point to the Sun, which meant there was time to prepare. The comet was entering the inner solar system at 61 kilometers per second relative to the Sun. To get a feel for that, a commercial airliner covers roughly 1/4 of a kilometer per second. 3I Atlas was moving more than 200 times faster. By the time it swung around the Sun on the 29th of October 2025, gravitational acceleration had pushed that speed to about 250,000 kilometers per hour, the highest ever recorded for any visitor passing through the solar system. And its trajectory, by an unusual quirk of geometry, sat almost inside the flat plane where the planets orbit, though running in the opposite direction to them. That's called a retrograde path, and it meant the comet was going to pass close to several of them on the way through. Mars came first, just 29 million kilometers away on the 3rd of October. Then perihelion at the end of October, tucked just inside the orbit of Mars at roughly 1.36 astronomical units from the Sun. Then outward past Venus, past Earth at 270 million kilometers in December, and finally past Jupiter in March 2026, before heading out of the solar system for good. That trajectory turned into an opportunity that the space agencies grabbed with both hands. ESA's JUICE spacecraft, which was on its way to Jupiter and was never designed to study comets, happened to be positioned closer to 3I Atlas than any other probe right around perihelion. Normally, planning an observation campaign for a deep space mission takes about 9 months. The team had 4. Angela Dietz, JUIC's spacecraft operations manager, later described the timeline bluntly. The planning had to be finished by the end of September, and the commands needed to be uploaded by mid-October. There was no margin. They activated 5 science instruments and squeezed the observations into 6 45-minute windows and 1 final 4-hour slot, all constrained by the spacecraft's thermal limits because JUIC was close to the sun and using its main antenna as a heat shield. In total, those windows generated 126 science files holding 11.18 gigabits of data. And then, the team waited because JUIC was far from Earth on the other side of the sun, transmitting through a smaller backup antenna at a fraction of the normal data rate. The data did not reach Earth until 2 downlink passes in February 2026, 3 months after the observations were taken. There's a specific engineering irony here. JUIC is a mission designed to survive the harsh radiation and cold of the Jovian system, and yet its observations of 3I Atlas were bottlenecked by heat and by bandwidth. The spacecraft was pointing its high-gain antenna at the sun as a parasol, so it had to talk to Earth through a low-rate backup channel. That's why we watched the perihelion in near real time from telescopes on Earth, but didn't see the sharpest close-in view of the coma until months later. It was the classic bandwidth versus latency trade-off. JUIC was far from alone. NASA coordinated Hubble, Webb, TESS, SWIFT, and SphereX from orbit. Europa Clipper, still on its way to Jupiter, swung its ultraviolet spectrograph toward the comet for 7 hours on the 6th of November. Around Mars, 3 spacecraft looked up at once. MRO's high-risk camera, normally pointed straight down at the Martian surface, rotated to face outward and captured the comet's coma as a pixelated white ball at 30 kilometers per pixel. Maven caught the hydrogen streaming off it in ultraviolet light, and on the ground at Jezero crater, the Perseverance rover pointed its Mastcam-Z at the Martian night sky and recorded a faint smudge barely perceptible against the background stars from 30 million kilometers away. Everything was in place. The question now was what the data would actually show. The major spectrometer aboard JUIC was designed to study the icy moons of Jupiter, and it had never looked at a comet before. But on the 2nd of November 2025, 4 days after 3I Atlas swung past its closest point to the sun, MAGIS caught something. The comet was releasing water vapor at a rate of 2,000 kilograms every second. That sounds like a lot, and it is. But active comets near the sun can produce enormous amounts of gas, so the volume alone wasn't the strange part. What caught attention was where the vapor was coming from. JUIC's submillimeter wave instrument confirmed that most of it was pouring off the sun-facing hemisphere, which made sense, but a chunk of it was also being released by tiny icy grains drifting through the coma itself. Those grains were behaving like miniature comets of their own. Each one sublimated as sunlight warmed it, and each one added its own gas and dust to the expanding cloud around the nucleus. The distinction matters. When ice sublimates directly off the nucleus, what you measure is essentially a surface signal, already partially reworked by billions of years of cosmic ray exposure. When it sublimates off free-floating grains inside the coma, you're looking at material that was locked deep inside the body until moments before. Pristine ice from the interior, thrown loose by the same jets that shed the grains. 2 different reservoirs, 2 different chemical fingerprints, 1 telescope pointing. The Janus camera aboard JUIC captured what that activity looked like up close. The images, which did not arrive on Earth until February 2026, revealed an extended coma with structure running through it. Jets of gas punching outward from the nucleus, filaments threading through the dust, and rays fanning out across the tail. Pasquale Palumbo, the principal investigator for Janus, described the images as showing the comet's intense activity right around perihelion. The comet was alive in a way that Oumuamua never was, and it was giving scientists far more to work with than Borisov ever could. Then the chemistry started coming in, and things got genuinely strange. In March 2026, A team using the Atacama Large Millimeter Submillimeter Array in Chile published their analysis of two molecules in the comet's coma: methanol, a simple alcohol, and hydrogen cyanide, a nitrogen-bearing organic molecule that shows up reliably in comets throughout our solar system. ALMA had observed 3I Atlas on two separate dates in late 2025, and on both occasions the ratio of methanol to hydrogen cyanide was far beyond normal. The two measurements came in at roughly 70 and 120. For context, the average across solar system comets sits around 26. In the entire historical record, only one known comet, C 2016 R2 Pan-STARRS, had ever produced ratios in the same ballpark. 3I Atlas was, by a wide margin, one of the most methanol-rich comets ever studied, and it had formed around a completely different star. The way the methanol was escaping told its own story. Hydrogen cyanide appeared to be coming almost entirely from the nucleus, which is what scientists typically see in comets close to home. Methanol, on the other hand, was streaming from the nucleus and from the icy grains in the coma, the same grains that were also releasing water. Those grains were carrying a chemical record of the comet's interior, material that had been locked in ice since before our sun existed, now sublimating for the first time in billions of years. Nathan Roth, the lead author of the ALMA study, described the observations as being like taking a fingerprint from another solar system. A few months earlier, in December 2025, the James Webb Space Telescope had already added another layer. Webb's MIRI instrument, which works in mid-infrared wavelengths between 5 and 28 micrometers, observed 3I Atlas on two occasions as the comet moved away from the sun. Those observations produced the first mid-infrared chemical fingerprint ever obtained from an interstellar object. And embedded in that fingerprint was something no one had seen before on a visitor from outside the solar system: methane. Webb also picked up water, carbon dioxide, carbon monoxide, and methanol, and the ratios between all of these molecules pointed consistently toward a formation environment colder and more distant from its parent star than anything in our own cometary archive. And then there were the X-rays. In late November 2025, JAXA's X-RISM satellite turned its soft X-ray telescope toward 3I Atlas and picked up a faint glow spreading outward from the comet's core. The emission filled a region roughly 400,000 kilometers across, about the distance from the Earth to the Moon, and it marked the first time an interstellar object had ever been detected in X-ray light. A week later, ESA's XMM Newton Observatory confirmed the detection with a separate 20-hour observation on the 3rd of December. The glow was produced by a process that scientists have understood since 1996, when comet Hyakutake first surprised everyone by shining in X-rays. Highly charged particles in the solar wind slam into neutral gas molecules streaming off the comet, and the collision transfers energy that gets released to soft X-ray photons. It is a well-known mechanism in solar system comets. No one had ever confirmed it happening in material from another star system. The spectral signatures embedded in that glow carried traces of carbon, nitrogen, and oxygen, atoms that are nearly invisible at optical and ultraviolet wavelengths, which meant the X-ray observations were revealing parts of the comet's composition that no other instrument could easily reach. Every new wavelength, every new instrument, every new molecule added to the same emerging picture. The material coming off 3I Atlas looked like cometary outgassing in its mechanics, but the proportions were off. The chemistry was unfamiliar, and the deeper anyone looked into the composition of what this object was shedding, the clearer it became that the ice locked inside it had formed under conditions profoundly different from anything in our solar system's history. The most dramatic confirmation of that was still sitting in the ALMA data, waiting to be published. What does it actually mean when scientists say the water was anomalous? Every water molecule is built from the same basic recipe: two hydrogen atoms bonded to one oxygen atom. Simple enough, but hydrogen comes in more than one version. The common form, the one that makes up nearly all the hydrogen in the universe, has a single proton in its nucleus and nothing else. There is a heavier version, though, called deuterium, which carries a neutron alongside that proton. It is still hydrogen. It still bonds with oxygen to make water, but the extra neutron gives the atom more mass, and when a deuterium atom takes the place of a regular hydrogen atom in a water molecule, the result is what chemists call semi-heavy water, or HDO. Every comet in our solar system contains some of this heavy water mixed in with the ordinary kind. Earth's oceans contain a small amount too. The ratio between the two, how many deuterium atoms show up relative to regular hydrogen, is one of the most useful measurements in all of planetary science, because that ratio acts as a kind of thermometer. It records the temperature of the environment where the ice originally formed. The chemistry behind it is straightforward. In the cold, dense regions of a young planetary disk, the reactions that swap a regular hydrogen atom for a heavier deuterium atom run faster when temperatures drop. The colder the birthplace, the more deuterium gets locked into the ice. So, when you measure the DH ratio in a comet, you are essentially reading a frozen record of how cold it was in the part of the disk where that comet's ice first crystallized, potentially billions of years ago. In solar system comets, that ratio clusters within a fairly narrow range. It varies a bit depending on whether a comet formed in the outer reaches of the Kuiper belt or closer in near Jupiter, but the numbers stay within the same general neighborhood. Earth's oceans sit at a particular value. Solar system comets sit somewhat higher. The spread is real, but it is bounded. Everyone working in this field had a good sense of what the upper end of that range looked like. 3I Atlas broke through the top of it and kept going. In April 2026, a team led by Luis Salazar Manzano at the University of Michigan published their analysis of ALMA observations taken just 6 days after perihelion. The HDO to H2O ratio they measured was at least 30 times higher than what has been recorded in comets from our own solar system, and roughly 40 times higher than the ratio found in Earth's oceans. The numbers were so far outside the known range that Salazar Manzano described the result as evidence that the conditions that led to the formation of our solar system are much different from how planetary systems evolved in different parts of our galaxy. 2 months later, a separate study led by Martin Cordiner arrived in Nature with JWST and ALMA data that pushed even further. Cordiner's team measured the DH ratio at 0.98%, plus or minus 0.06%, which is more than 10 times higher than any comet previously known. They also found that the carbon isotope ratios in CO2 and CO were anomalous, with the proportion of carbon-12 to carbon-13 landing between 141 and 191, well above typical values found anywhere in the solar system in nearby interstellar clouds, and even in the protoplanetary disks that have been studied around other young stars. Everything in the comet's isotopic profile pointed in the same direction. The ice inside 3I Atlas had formed somewhere extraordinarily cold. The deuterium enrichment is consistent with temperatures hovering around 20 Kelvin, which is roughly minus 253 degrees Celsius, in the frozen outer reaches of a protoplanetary disk surrounding a star that no one has been able to identify. Teresa Panecki Carreno, a co-author on the ALMA study, put it simply, each interstellar comet brings a little bit of its history, its fossils, from elsewhere. We don't know exactly where, but with instruments like ALMA, we can begin to understand the conditions of that place and compare them to our own. That comparison is what makes the measurement so significant. Planetary scientists have spent decades measuring deuterium ratios in solar system comets and using those ratios to reconstruct the temperature profile of the disk where our planets formed. Those measurements have taught us a lot, but they've all come from the same system, the same disk, the same starting chemistry. 3I Atlas offered something the field had never had before, a direct isotopic sample of water that crystallized around a different star under different conditions, in a different part of the galaxy. It's the first time anyone has been able to read that particular chemical record from another planetary system. And the answer that came back was that this comet's ice formed somewhere far colder, far more deuterium-rich, and far more chemically distinct from our own solar system than the standard models predicted. One consequence of that result cuts directly into an old debate. For decades, planetary scientists have argued about how much of Earth's water was delivered by comets versus asteroids, using the DH ratio as the arbiter. Most solar system comets carry too much deuterium to match our oceans, so the current consensus leans toward the water arriving mostly on carbonaceous asteroids, which sit closer to the terrestrial value. 3I Atlas complicates that story. If the DH ratios of interstellar objects vary this widely, the assumption that cometary water has one characteristic signature doesn't survive contact with a larger sample. Different disks, different chemistries, different possible water reservoirs. The question of where Earth's water came from doesn't change, but the framework for asking it about other planets just widened. Our solar system is 4.5 billion years old. The Sun, the planets, every asteroid and comet and grain of dust orbiting within it all condensed from the same cloud of gas and shared the same starting chemistry. 3I Atlas did not come from that cloud. And according to the isotopic evidence, it may have been drifting through interstellar space for longer than our solar system has existed. The carbon told the story. Carbon-13, a heavier isotope of carbon, accumulates gradually in the interstellar medium over time as successive generations of stars live and die and seed the galaxy with processed material. A low abundance of carbon-13 relative to carbon-12 means that the material in question formed early, before the galaxy had time to build up its modern levels. Cordina's team measured the carbon isotope ratios in the CO2 and CO streaming off 3I Atlas and found values well above what exists anywhere in the solar system today, which, when run through models of how the Milky Way's chemistry has evolved over its lifetime, pointed to a formation window roughly 10 to 12 billion years ago. The universe itself is only 13.8 billion years old. If the estimate holds, 3I Atlas formed during a period astronomers call cosmic noon, the era when star formation across the Milky Way was at its most intense, when young planetary systems were assembling everywhere, and when the galaxy's chemistry was still sparse and metal poor compared to what it looks like now. The star that this comet originally orbited may have burned through its fuel and died billions of years before our own sun ignited. The planetary system where this ice first crystallized may no longer exist in any recognizable form. Every geological sample we have on Earth is younger than the Earth. Every meteorite in every museum collection is younger than the Sun. The oldest solid material ever measured, calcium aluminum inclusions in primitive meteorites, dates back to about 4.567 billion years ago and defines the moment our solar system began. 3I Atlas may predate that moment by a factor of 2. If the age estimate is correct, this is by a wide margin the oldest object any human being has ever measured directly. That needs a caveat, and the caveat matters. The age estimate is built on isotope ratios fed through models of galactic chemical evolution, and those models carry their own uncertainties. Cordina's team acknowledged that there could be edge case scenarios offering different explanations for the unusual composition. The 10 to 12 billion year figure should be understood as the best current interpretation of the data, arrived at carefully and published in Nature. But it is a scientific estimate rooted in a chain of reasoning that future discoveries could refine. There is also the question of what billions of years of wandering through open space does to a comet's surface. A 2026 study by Maggiolo and colleagues proposed that prolonged exposure to galactic cosmic rays, the high-energy particles that fill interstellar space, gradually altered the chemistry of 3I Atlas's outer layers over time. Radiolysis can break apart water molecules and recombine them into new compounds, which means the surface chemistry that instruments measured during the comet's pass through the solar system may not perfectly represent the pristine interior. The Subaru telescope's observations from January 2026 lent some support to this idea. The CO2 to water ratio, measured in the coma after perihelion, when outgassing was probing deeper into the nucleus, came in lower than what space telescopes had measured earlier. The deeper you look, the more you may be reading the original recipe rather than the cosmic ray-weathered crust. All of this is still being worked through. The datasets from JWST, ALMA, JUICE, and the rest are large and complex, and the papers are still coming. Instrument teams across multiple space agencies are cross-referencing their observations, and detailed publications are expected to continue through 2026 and beyond. The science of 3I Atlas is not finished. It is, in many ways, just getting started. And the next chapter is already being written by hardware that either exists or is under construction right now. The Vera C. Rubin Observatory in Chile has already demonstrated what it can do. During its science validation phase, Rubin's LSST scan captured images of 3I Atlas as early as the 21st of June 2025, 10 full days before anyone knew the comet existed. Those images were sitting in the pipeline as background noise until the Atlas discovery told the analysts what to look for, at which point the earlier data became pre-discovery observations that helped refine the orbit. Once the observatory begins its decade-long legacy survey of space and time, its enormous field of view and rapid cadence could detect dozens of interstellar objects over the survey's lifetime, with some estimates running as high as 50 to 70. There are thought to be roughly 10,000 interstellar objects drifting through space inside Neptune's orbit at any given moment. We have found 3. That number is about to change. Then there is Comet Interceptor. ESA is building a spacecraft designed to do something no mission has done before. Launch, park at the L2 Lagrange point, about 1.5 million kilometers from Earth, and simply wait. Its primary target is a pristine comet arriving from the Oort cloud for the first time, something untouched since the dawn of the solar system. But the mission team has always had a second scenario in mind, one they describe as unlikely but deeply appealing: an interstellar object on an accessible trajectory. When Comet Interceptor was selected in 2019, only one interstellar object had ever been found. Now there have been 3, and the diversity between them has been enormous. Michael Kuepers, the mission's project scientist, has said that visiting one could provide a breakthrough in understanding their nature. The spacecraft is scheduled to launch in 2029. For those who followed the Breakthrough Listen campaign, the answer there was clean and definitive. Multiple radio telescopes, including the 100-meter Green Bank telescope at a sensitivity of roughly 0.1 watts, search for artificial signals from 3I Atlas across a wide range of frequencies. Meerkat detected hydroxyl, a natural product of sunlight breaking apart water ice and nothing else. No technosignatures were found at any wavelength by any instrument. The comet is a natural object, a frozen remnant of another world's formation. And in its own way, that makes the chemistry it carried more remarkable, because the strangeness of 3I Atlas does not require an exotic explanation. It requires only that the universe is large enough and old enough and varied enough to produce ice with a chemical fingerprint that nothing in 4.5 billion years of solar system history can match. For most of human history, comets were local phenomena. They came from the Oort cloud or the Kuiper belt. They swung around the sun, and they either came back on schedule or disappeared into the outer darkness of our own system. Everything about them, their ice, their dust, their volatile chemistry, belonged to the same 4.6 billion-year-old story that produced the Earth, the Moon, and every living thing on both. 3I Atlas did not belong to that story. It carried water that crystallized at -253 degrees Celsius, in the outer reaches of a protoplanetary disk orbiting a star no one can name, in a region of the galaxy that was still chemically young, during an era when the Milky Way was forming stars at a rate it would never reach again. That ice survived the death of whatever system produced it, drifted through interstellar space for something on the order of 10 billion years, crossed paths with our sun purely by gravitational coincidence, and for a few months in late 2025 and early 2026 began to warm. The ancient volatile compounds locked inside it sublimated into gas. The gas streamed outward, and the instruments that humanity had positioned across the solar system, some of them on other planets, some of them on spacecraft sailing between worlds, read the chemistry of that gas and found a composition unlike anything ever recorded. 2,000 kilograms of water vapor per second, and every molecule of it carrying a deuterium signature that placed its origin in a colder, older, and more chemically foreign environment than any ice ever measured in our neighborhood. Methanol at record concentrations. Methane detected for the first time on an interstellar visitor. An X-ray glow produced by gas that had been frozen since before the sun was born, now colliding with the solar wind for the first and only time. The comet is past Jupiter now, heading outward through the constellation Gemini, at a speed that will carry it beyond the planetary region of the solar system by the early 2030s. It will keep going. It will not slow down. It will not loop back. Whatever it still holds inside its nucleus, whatever deeper layers of pristine ice remain untouched beneath the cosmic ray-weathered surface, will stay frozen and unread, carried back into the interstellar dark by the same momentum that brought it here. All of the data has been collected. The observation windows are closed. What remains is the analysis, and that will continue for years, because the chemical information embedded in those 126 science files from JUICE in the ALMA spectra, in the JWST infrared maps, in the X-ray images from XRISM and XMM Newton, contains more about the formation conditions of another planetary system than the field has ever had access to from a single object. No single observation settled anything on its own. The Magis water measurement by itself would have been unusual but not conclusive. The ALMA-methanol ratio in isolation could have been shrugged off as one weird comet. The X-ray glow only made sense once you knew the composition of the coma. The minus 253 degrees Celsius formation temperature only emerged once you combined the deuterium chemistry with the carbon isotopes and the molecular ratios. The 10 billion year age only stood up because the trajectory reconstructions agreed with the isotope models. The picture assembled itself from readings that individually meant little and together meant a great deal. That's how a lot of modern science actually works. Not one instrument answering one question, but a distributed set of measurements across wavelengths, disciplines, and continents, converging on an answer none of them could reach alone. 3i Atlas was not sent. Nothing about its passage through our solar system was inevitable. It was a frozen leftover from a world that assembled roughly 10 billion years ago, ejected by some gravitational interaction we will never reconstruct, set adrift in a galaxy where the spaces between stars are so vast that the odds of any given object passing close to any given sun are vanishingly small. It happened to pass close to ours at the precise moment in our technological history when we had the telescopes, the spacecraft, the spectrographs, and the coordination to catch it, read it, and understand at least some of what it was telling us. There are thousands more out there right now, drifting between the planets, too faint and too small for current surveys to find. That is about to change. And when the next one arrives, we will know far better than we did a year ago what to look for in the chemistry of its outgassing, because a single ancient visitor passing through once gave us a language for reading ice that formed around other stars. The question now is what the next one will say.